In section 4.3, we look at prime and composite numbers. Okay, so we start by defining prime and composite numbers, and then we actually start, instead of determining whether a number is prime or composite, we start by verifying a number is prime. So we're given numbers that are prime, and instead of them having to determine whether it's prime or composite, they have to go straight to this is prime, show or prove that it's prime. Okay, and the reasoning behind this is typically students, when it comes to prime numbers, they think if it's odd and they can't think of a factor, then it's probably prime. So we want them to have a process to do this, a rigorous process that truly shows whether a number is prime or not. Okay. Notice here we have a table of prime perfect squares. Basically the idea behind this, let's look at 163. Okay, so if we want to determine whether 163 is prime or not, okay, we just need to see, based on the fundamental theorem of arithmetic, whether it has any prime factors less than the square root of the floor. Okay, so 163, again, I wouldn't tell your students that, but I'm just trying to show you guys the idea. The square root of 163 is 12-ish, where the floor is 12. Okay, so that means the prime numbers less than 12 are 2, 3, 5, 7, and 11. So to verify that 163 is prime, they just have to show that dividing 163 by any of these numbers results in a non-zero remainder. Okay, so I think the table of prime perfect squares is useful for this. We don't want them to have to check 2, 3, 4, 5, 7 all the way up to 12. Okay, and you can make some justifications of why this is. So if a number was divisible by 6, we don't have to check that because it would have already been divisible by both 2 and 3, etc. Okay, but this streamlines this process of verifying whether a number is prime or not, and they don't have to check every single number. And again, they usually think they have to check up to half the amount instead of the square root. So they divide 163 by 2 and can start making a list up to 80, which is, of course, not useful. Okay, so for 89, it lies between 49 and 121. So the smaller of those two numbers squared is 7. Okay, so to verify whether 89 is prime, they have to check 2, 3, 5, and 7. Then we give them some numbers and have them determine whether they're prime or composite. Okay, and so here they basically follow the verifying a prime number process from the last example. Okay, but if along the way they get a factor, then they can just list that one factor pair and say the number is composite. So notice with 27, just looking at the largest you'd have to check, 27 is between 5 and 7, so you just have to check 2, 3, and 5. And again, that one's easier. It's divisible by 3, and most people know that. For 91, let's just do one of these. For 91, to see whether it's composite or prime, you'd have to see if it's divisible by 2, 3, 5, or 7. Okay, and I think in the videos we just do division and check for remainders. If there's a decimal expansion, then it's not a factor. Okay. So yes, they should know it's not even, so that doesn't work, but verifying that is okay. Checking 3, it's not divisible by 3. 91, it doesn't end in 0 or 5, so it's not divisible by that. And dividing by 7, lo and behold, 91 is 7 times 13. Okay, and notice I intentionally picked this one in this section because 91 is one of those numbers. It's odd. You can't think of a factor off the top of your head likely. This isn't in our multiplication tables, so they may think it's prime, but they need to follow the entire process of checking all of these to realize that it is in fact composite. Okay. Then we have prime factorization, and we use number trees or factor trees. You can also use repeated division method. I think the factor trees work pretty well. One thing that's important is we want them to write in factored form and exponential form, and we have them in general write these in increasing order. So just for 12, okay, 3 times 4, 2 times 2. I have them circle when the branch ends in a prime. Okay, so the factored form in increasing order is 2 times 2 times 3. The expanded form is 2 squared times 3. So this helps them start to use their exponential notation and again connect that to the expanded form or factored form notation. Okay. Okay, and let's start a new video.